Okay, I am going to talk about structured prediction with local dependencies this time. We're going to talk about CRFs. The reading material had a lot of information, I think, and obviously it had 100 more pages that you didn't read. So I'm going to be trying to talk a little bit about the 100 more pages, trying to connect it back into the reading material that you had here and explain how these are used in modern methods. That being said, I think the reading material there is actually pretty nice if you want to go through all 100 pages of it. So, feel free to do so if you are interested in this topic. So, another thing is this is really going to get into our discussion of like structured prediction problems and kind of more interesting structured prediction models. And up until now, we've talked about a lot of prediction problems. I hate this movie, I love this movie, going to very bad and very good. And so this is one example of a prediction problem where you get an input and you want to predict an output. But there's lots of different types of prediction. The first one being binary classification, where it's I hate this movie going to negative, or I hate this movie going to very bad. So this would be multi-class classification, where we don't only have two classes. And then the final one would be an exponential or infinite number of labels. So this would be a structured prediction problem. So this could be anything from going to I hate this movie to parts of speech. And parts of speech themselves are not an infinite number of labels, but the part of speech sequence combinatorially is an exponential number of labels at least. And then going from language to another language, this also is kind of an infinite output space, or at least a very large exponential output space.
Excuse me?
Yeah.
Oh. Next slide.
Yeah?
You're answering my question.
Okay. Yeah. So why do we call it structured prediction? And this is a little bit difficult because you might not think of a part of speech sequence as a structure, or might not think of another sentence as a structure, for example. However, and the things you might think of as structures are like trees or graphs or something like this, what we're going to be talking about in the next thing. Sorry, that should be two, TOO. So the problem here is that the classes are too numerous to enumerate. So there's no way that you could actually enumerate all of the possible outputs and calculate, for example, a loss with respect to all of them. And because of that, you need to use some sort of method to exploit the underlying structure of the input or output space, usually output space, to try to make this a tractable problem. So because of this, you need some sort of method to exploit the problem structure. You need some sort of method to say, it's not just all of these classes that we're going to be independently predicting, but rather we need to consider, hey, a sentence is a bunch of different words that fit together, or a bunch of different characters that fit together, etc. So an example, to give an example of this, anybody in this class would look at these two inputs and say, hey, these two inputs are similar, right? They have outputs. They have three parts of speech that are different and one part of speech that's the same. And because of this, it's not the case that you would say, oh, this is completely different than this, and we need to, predict these differently. You can say, oh, I can do some sort of intelligent computation to make this more tractable. So that's the whole idea, the general idea behind structured prediction. And there are many varieties of this. There are many different models. So one could be like an RNN-based decoder. And the way the RNN-based decoder exploits problem structure is by calculating the output one at a time and feeding it back in when you calculate the next representation. Convolutional self-attentional decoders, same thing. They're calculating one at a time and outputting. Or, for example, conditional random fields with local factors. There's lots of training algorithms. So training algorithms could be maximum likelihood with teacher forcing, which we've talked about a lot so far. Sequence level likelihood with dynamic programs. We're going to talk about that today. Reinforcement learning, minimum risk training, structured perceptron, structured large margin, or some sort of heuristic approximation to these methods. And basically, we've covered these ones already. So we've already covered some structured prediction algorithms. And we're going to cover these ones today. So this is a different approach.
Oh, what is teacher
Yes.
forcing?
Oh, teacher forcing. So I'm going to talk about it in a second. So maybe I'll just wait for the slide. So an example structured prediction problem. So one example of a structured prediction problem would be sequence-sequence modeling or translation. I'm going to talk about a different one, which is sequence labeling this time. Oops. And sequence labeling is basically where we want to output one tag for each word. One example would be part-of-speech tagging. So part-of-speech tagging is a more common, a very straightforward application of sequence labeling, where we literally have one tag for each word, and that tag has some idea of, or gives you some idea of the features of the word. Another example of this would be, yeah, actually maybe I'll skip that because there's actually many more good examples of the second thing, which is named entity recognition. So named entity recognition isn't exactly a word-to-word labeling problem, it's a span labeling problem. Basically what you want to do is you want to label Keanu Reeves as a person, basically, and this is a two-word span. But you can formulate it as a word-by-word sequence labeling problem using BIO tags. And I think this was covered in the reading, right? So basically, you take the you take this and you put the first word as B, the second word as I. There are other ways to approach this, and maybe I'll talk about them very briefly at the end of the talk, where you actually treat spans as spans. This way is most common simply because it's simple. You can apply other sequence labeling methods, etc. Okay, so why do we want to do a structured prediction in part-of-speech labeling in the first place, or sequence labeling in the first place? And the answer is that consistency in your outputs is important, and it can give you a hint about how you can create better models. So one example of this is you have time flies like an arrow. This is a famously ambiguous sentence. So what is the part of speech of time in the most famous interpretation of this thing? The kind of metaphor, the metaphor here. Noun, okay. What about flies? Verb, yeah. Preposition. Okay. Yeah, so that's pretty good. If you take the part of the Wall Street Journal tree bank annotation, it's like noun, verb, a particular type of preposition labeled IN, determiner noun. So yeah, that's pretty obvious. Okay, so what's another interpretation of this? So what would, it could be an adjective, maybe. And then what would flies be? Noun, okay. Let's see if that's the actual one I have, yeah. So I think that would actually be a noun phrase. It wouldn't be an adjective, but you had the right idea. So this is time flies. It's like a special type of flies that are like time flies. And they really enjoy arrows. So that's the interpretation there. There's a final interpretation that's still a very grammatical English sentence. Time is a verb, yep, yeah. So the command form. So you're telling somebody time flies like you would time an arrow, basically. So we have all of these interpretations, right? And they're kind of, strange interpretations here. So let's say we didn't consider the interaction between all of these, and actually each one of these interpretations was equally likely for whatever reason. What would happen? You take the most common one, or you take the most likely one. Oh yeah, there are the interpretations there. And you take all of them together, you do voting over these, and you get time flies like an arrow. So basically, this now becomes something completely different than any of the things you predicted. It becomes time flies that are similar to an arrow. Time flies, the noun phrase, which is similar to an arrow. So you can see that despite the fact that all of these are like similarly likely, you wouldn't get any of the coherent outputs that you would have expected if you just make all of these predictions individually. This is a somewhat contrived example. It's even worse for things like sequence models where you're trying to generate text because text is really dependent on the neighboring words, etc. So what we can do is we can forget about what I just said in the last slide and instead do independent classification. So basically, we would calculate a word embedding for each of these words, and then we would take a classifier. Let's say we had a CNN-based classifier that took in all the neighboring words, and we calculated each of these one at a time. So this is a perfectly reasonable way to solve this problem. For problems like part-of-speech tagging, it's actually not a bad thing. One of the papers that I wrote when I was in my master's degree actually said, hey, this is relatively competitive with more complicated models like CRFs, but it has advantages with time and ease of training on partially annotated data, et cetera. So like for kind of simpler tasks like part-of-speech tagging, it's actually not a horrible idea to do something like this. So this is a structured prediction task, but not a structured prediction model. It's multi-class classification. So what does this look like when we talk about this in CRF land? What does it look like when we talk about it in like the factor graphs that you read in your reading? It basically looks something that's a little bit like this. Here. And then something a little bit like this. VBP. And so basically what you're doing is you're saying we have independent factors that each rely on the word itself and the two words around it, and we're calculating an output based on this. So now what does a BIOL-STM look like? A BIOL-STM looks like this and calculates the output. So is this how does this relate to a CRF or whatever we were talking about in factor graph land in the reading? This is an interesting thought experiment. Is this a quote-unquote structured prediction model?
It is taking features from all the words.
Mm-hmm. So the input is taking features from all of the words in the sentence. Yeah, so that's basically it. So if I wanted to draw it as a factor graph, what would it look like? It would basically look like this. Right? So we have the BIOL-STM passing information from all of the words in the input. However, we don't have any connection between these two, right? We're still just calculating features from the input. We're calculating the output, and all of these outputs are being calculated independently. So this is still not modeling the output structure. It might be modeling, implicitly modeling the structure of the input, but hey, so is a CNN. It's just, this is doing it over the whole sentence, whereas the CNN is doing it over, only a part of the sentence. So is this clear? Okay. So now let's think about something else. Let's think about how we, what would happen if we made a recurrent decoder. So I have the backward LSTM in here just to demonstrate that this is something you could still do in this case. But we have the forward LSTM. It takes in an input, takes the output, calculates the vector here, makes a prediction, takes the output, calculates a vector here. So now, is this a, like, quote-unquote structured prediction model? Yes, yeah. So I would agree with you. And the reason why is basically the probability of the next one depends on the probability of the first one here. Maybe implicitly the probability of all of them depends on the joint probability of all of these together. Yes.
Quick question, in that over there on the LSTM, how do we know if we're predicting the label of the first word or the second word?
How do we?
I guess it was the previous slide.
Okay. How do we know if we're predicting the label of the first word or the second word? So that's a good question. Oh, here?
Yeah.
So basically, this is a factor graph, and the factor graph is telling you like what the output variable depends on. But in reality, what you're doing is you're taking, in like implementation-wise, what you're doing is you're taking these two vectors, and these two vectors are strongly associated in the backward direction with I, and strongly associated in the forward direction with this. So with I also. So basically, by taking these two vectors, the last word you've seen is I, so you know that's the word that you're actually predicting right now.
But from the factor graph, there would be no difference?
So one thing you should note about factor graphs is factor graphs are describing dependencies. They're not describing that this and this are the same calculation. They're basically just saying these are the statistical dependencies between the variables in our input and output. They're not saying that we're going to be doing the same calculation over all of these variables. That's a good question, though. Any other questions? No? Okay. So now we have this recurrent decoder. This is, I guess one way you could think of this is has like a directed edge between these two. I'm pretty sure this is right. Actually. So you basically have a directed edge where the probability of VB P depends on this. Yeah.
In this case, is the tag or the label directly influencing the representation of this, or should there be a separate arrow? For example, at PRP, does it go as a separate arrow to the classifier, or does it influence the hidden representation itself?
I mean, it could do both. So the question was, does PRP directly influence the classifier, or does it go into the representation? The answer is you could do either. It doesn't matter. It's a neural network, so you can design it however you like. The most traditional way, though, is definitely to feed it into the hidden state of the decoder.
But in that case, then essentially, when you're predicting a tag, it also depends on all the other tags, right? Not just the previous tag. Because let's say the
yes, yeah, you're right. So it would depend. It would be something like that also. Yeah, that's good. Any other questions? So basically, this is a structured prediction model. This is one way you can make a part of speech tagging model, for example. But there's a couple problems with these various approaches. So independent classification models, strong independence assumptions, no guarantee of valid or consistent structures. I think I've already expressed this well enough. History-based and sequence models, though, have their own problems. The first one is that there's no independence assumptions. So, so this isn't necessarily a problem. That's maybe a good thing. But because of this, there's no way to exactly calculate. And like if you want to calculate the maximum probability output sequence, you have to do this through beam search or something like this. If you want to do training that explicitly tries to maximize the probability of the output sequence in a kind of unbiased way, you need to do reinforcement learning or minimum risk training or something like this that I'm going to be talking about later. And exposure bias is another problem. So what do I mean by exposure bias? So here's where I get to talking about what teacher forcing is. And teacher forcing is basically, kind of the standard way of training language models or translation models, sequence models or whatever. And basically the system is trained receiving only the correct inputs during training. So when you calculate the probability of the next word or in this case, I guess it would be the probability of the next tag. In a language model, it would be calculating the probability of the next word. You calculate it based on the correct words that you've seen in the past. And then what exposure bias is basically at inference time, when you actually want to be predicting outputs, you might actually not be being fed the correct part of speech tags. Like you might make a mistake in a previous part of speech tag. However, your model has never been exposed to these errors because it's never seen wrong sequences before in the input. So basically it fails. Yeah, did you have?
Couldn't you intentionally inject errors?
Couldn't you intentionally inject errors? So yeah, this is one method for training that we're going to be talking about.
Excuse me?
Yeah.
What is a correct input? Input is always correct, right?
So this, sorry. Okay, sorry. It's the correct outputs. So this is a little bit confusing. So basically, like, it's the correct output labels. Like in this case, it would be PRP, VBP, DT, NN. And the reason why I wrote input, which is I acknowledge confusing, I'm sorry about that, is these outputs are then input back into the models. So basically, it's both an output that you're predicting and an input to the model in like an RNN-based model. Does that make things clear?
So
Yeah.
when you're saying that it's going to input only the correct output or whatever,
Mhm.
the ones which are correct, does it mean the ones which it's predicting with a high enough confidence, or
So,
is there some threshold by which you can
So for standard training in neural language models, neural translation models, a neural part of speech tagger that uses previous outputs, the standard way of doing it is at training time, you just feed in the actual tags. You feed in the actual words. You don't make any predictions at training time. There are alternatives to this, injecting noise at training time, which actually we're going to talk about, I think not this time, but next time. The standard way that you would do it if you weren't doing any special tricks is just feeding in the correct inputs. Good questions though. Any other questions? Okay, so let's say instead we didn't get the correct output. We got VBG for whatever reason. Let's say the model hadn't seen hate before and thought it was a present progressive verb. It seems pretty implausible, but maybe it would do that. So then instead of that, it would, it gets the wrong tag and then it continues getting the wrong tag because it made a mistake previously. And it basically over relies on the previous inputs because it's never seen a wrong one before. So there's a bunch of different ways to fix this. I'm going to be talking about them like this class and then a few classes later. But one of them is conditional random fields. So the overall idea of models with like local dependencies in them is that you make some independent assumptions on the output space, but not entirely independent. So you have local dependencies on the output space. And the reason why you only have local dependencies instead of having more long-term dependencies like the one RNNs give you is this allows you to do dynamic programming algorithms to train your models. So this gives you exact and optimal decoding and training via dynamic programs. So one example of this is conditional random fields. And before I get into that, I'm going to talk a little bit about local normalization versus global normalization. And what I mean by local normalization versus global normalization is locally normalized models are the models that we've covered mostly up until this point. And these are models where basically, if you want to do something like calculate the probability of y given x for a particular sentence, or like a particular structured output space, like let's say we were doing machine translation or tag by tag sequence labeling, what you do is you calculate the probability of word number 1, and you calculate the probability of word number 2, you calculate the probability of word number 3, and you take the overall probability as the product of these probabilities. And the way you do this is you have a softmax at each time step, basically. So at each time step, you calculate a score. You take the softmax over that score with respect to your vocabulary, and then you multiply all of these together. However, these models are susceptible to something like exposure bias easily, precisely because okay, so sorry, I'll take a step back. The good thing about these models is that they're relatively easy to train. And the reason why is because you're taking your classification problem over an exponential or infinite output space and turning it into a sequence of tractable multi-class classification problems. So in the case of a machine translation model, for example, it would be multi-class classification over all the words in your output vocabulary. So that's good because we know how to do multi-class classification. We just take a softmax and try to maximize the probability of the output. However, what we actually want to do is make sure that the output, the overall best output that we get, that we want to output, gets the best score overall, or gets the highest probability overall. So globally normalized models, which are also called energy-based models in some cases, each sequence has a score, which is not normalized over a particular decision. So I'm sorry, this slide is left over from a previous explanation, so I'll write it in a different way on the board. But basically, a different way you can write this is the probability of y given x is equal to some sort of feature function over y and x, where you sum over all y in v star. So instead of summing over all words in the vocabulary, you're summing over all sentences that consist of 0 or more vocabulary items from your vocabulary. So this is kind of a nice way to formulate things because now we're thinking about just the score of the output, and we can kind of optimize the score of the output directly. The problem is this sum down here is intractable. There's no way to calculate it over an exponential space unless we do something clever. So, so conditional random fields are basically, globally normalized models, a variety of globally normalized models. And the general form of them basically looks like this. So it's essentially a factor graph where you have connections between all of the, all of the outputs. And then you have X. This is your BIOL-STM transformer, CNN, pick whatever you want. You calculate representations of X, and based on this, you calculate factors between the input and an output. So an RNN, another way to think of an RNN is you can think of like an RNN-based thing where you're taking the previous inputs as essentially a fully globally normalized model. But the problem with fully globally normalized models is we can't enumerate over them unless we make some assumptions about their form. So it looks like this. The first order linear CRF basically says we're not going to consider interactions between things that aren't neighboring in the output space. And by doing this, this allows us to actually enumerate and actually calculate the partition function. And specifically, the way we do it is with a form like this, which I'll elucidate in a moment. But basically, what you can see here is you can see that you consider two neighboring outputs, but you never consider the whole sentence at once.
Excuse me.
Yeah.
So yi's here, like you said, are the set of all possible sentences.
So big Y is the set of all possible sentences.
So like y1, y2, y3, can you give an example of what these are?
These could be part of speech for word number 1, part of speech for word number 2, part of speech for word number 3.
Okay, but the way we differentiated this form from the previous form, like after that, when you said this is like huge, is that was over at every step I'm going through all the words in the vocabulary. But in this case, we are doing what?
In this case, you would be going over all pairs of words in the vocabulary and calculating scores for them and multiplying them together, and only then are you normalizing.
In this case, first order linear CRF.
In this case, yeah.
But I'm asking about that case versus the old case.
So for this case versus the old case,
Yeah.
the globally normalized ones.
So for this case, you are considering all possible combinations of words, right?
Right. So in this particular case, the big difference here is a locally normalized model is doing normalization at each time step. This has no necessity to do normalization at each time step. It only does normalization after you've calculated the score for each like sentence itself. So you're calculating the score for the sentence, score for another sentence, score for another sentence, and then you're doing normalization over the sentence level scores. So globally normalized models, any locally normalized model is a globally normalized model, kind of by definition, because the necessity of a globally normalized model is that you're going to be multiplying these things together and then dividing by some scores overall. But you can kind of shoehorn a locally normalized model into this form as well. It's not easy to do the opposite. It's not easy to turn a globally normalized model into a
And one more question. Can you give an example of the intuition of the edge? Like what does the edge represent?
Yeah, so I'll give an example of that in a second, about what the edge represents. But basically it's dependencies between two neighboring part of speech tags would be one example. So like, is it likely that a noun comes after a determiner? If so, determiner noun would give you a higher score. But I'll talk about that in a second. Okay. So basically what we're going to want to calculate is potential functions. And potential functions are basically for each neighboring set of values here, how do we calculate a score? And the way you calculate the score is by calculating kind of an arbitrary score and then exponentiating so that this is positive, because the potential functions here need to be positive in order for this normalization to work. You can't have negative functions in a probability. So what you do is you calculate an arbitrary score and you exponentiate. Notably, you did not normalize yet. So you're just exponentiating these values. And importantly, there's kind of two different values. One is a quote-unquote transition function. And the transition function is basically the thing that calculates kind of interactions between two neighboring output scores. Neighboring output symbols. Also kind of from a traditionally, when people were using hidden Markov models, this was called an emission probability. Maybe emission is less good than like single tag or transition probability. So I guess S probably stands for single tag. And so what this is doing is this is just calculating the likelihood of a particular tag. So this is a more general form. And we can use like neural features where we calculate a neural featureizer and we have a weight matrix that looks something like this. I'm going to go to the simpler version first to just kind of explain what this looks like in the simpler version. And in the simpler version, what you do is you calculate a representation from your neural featureizer. Let's say it's a BioLSTM, and then you calculate a hidden vector. And then you multiply this by another vector. You take the dot product with another vector, which says, how likely is this part of speech tag to happen given all the information I know from my BioLSTM? So this is essentially like the weight matrix in your softmax. You can think of it this way. Where you have y1, y2, or sorry, yi equals 1, yi equals 2, y equals 1, y equals 2, y equals 3. And each of these factors corresponds to one part of speech tag. So it's basically like your standard score calculating weight matrix in a any neural model you have, the thing that you multiply before you put it into your softmax. The second thing here, this is a transition weight between I minus 1 and I, y minus 1 and I. So this will be a square matrix where the matrix is the size of the vocabulary, maybe the size of the tags, where very common transitions are going to have a high score. So like, for example, if this is the yi minus 1 part, and this is the yi part, if this is dt, determiner, and you have noun, this will have a high score, because nouns very often come after determiners. But if you had dt, this will have a very low score because determiners very, uncommonly come after determiners. So, so basically, it has these two components. It has the how likely is this in context component and the how likely is this transition going to be happening component. And then you also have a bias. This bias would be, I guess, over yi. So that would be a bias vector, just telling you that, hey, determiners are common, nouns are common, numbers or other parts of speech tags are less common. So these are kind of the three types of parameters you have in addition to your neural network. So this would be an output layer. Is this clear? Any questions about this? Yeah.
Sorry, basic, but what is f of xi?
What is f of xi? So this would basically be this hidden vector here. So you take an x and you calculate the likelihood of you calculate a representation for position number I. So if it's very likely to be a determiner in that particular position, this would be similar to the vector that you have for determiners, and you would get a high score for determiner there.
So the simpler version versus the previous one
Mm-hmm.
drops the f of xi.
So the more complicated version basically doesn't have a dependence of the transition probabilities based on the current hidden state. And the reason why is this is already pretty big, right? Like let's say you have 50 parts of speech tagged by 50 parts of speech, and if you further condition that on the hidden variable, this would now be a tensor, where essentially that would be the hidden state size. So it would be like 300 hidden states by 250, which starts to get like a lot of parameters to learn. Yeah. Good questions. Yeah.
When you said that x equal to 1 to 2 of softmax scores,
Mm-hmm.
like do we normalize them or can you also take the logic scores?
So this is like the logic scores for the softmax. It's not, you do not normalize them. That's actually the important thing about this here. Yeah, good question. Any others? Okay, I will continue. So this is what it looks like as kind of a graphical, if you put it as a graphical model type representation. So basically you have these going in to influence the factor here, and then you have all of these neighboring outputs influencing each other. So so this is what it looks like. The question now is, how do you train this, and how do you actually calculate outputs given this? This might be a little bit complicated if you haven't implemented training HMMs. I know that's one of the things in algorithms for NLP. So if you've taken that course, I think it should be simpler. If not, then maybe you can read the readings. But basically, what we want to do is we want to calculate this partition function, or we want to calculate the likelihood of the output and maximize the likelihood of the output given the input. What this looks like is this. So this is the thing that we had before. And now if we take the top and keep it the same and have the bottom be z of x, this is something that's easy to compute. So basically what we do is we just step through each output and calculate this for the gold standard output, for the actual true output. So each one of these individual things is easy to compute. There's no sum here, so that's no problem. However, the sum is a problem, right? Because we can't sum over all of our potential outputs. So this is hard to compute. This is the partition function. So how do we do this? And for training, we need to be able to enumerate to calculate this value. Also, at test time, when we want to calculate the best output, we similarly would like to do the argmax over y. And this also requires enumeration if we're not smart about how we do things. So either one of these would require us to do kind of complicated exponential calculation. So that's a problem. So the way we can do this is by noting that because things are only interacting locally, we can calculate this efficiently nonetheless. So the score of each label depends on the input and the nearby labels, but given adjacent labels, the other ones do not matter. So the scores do not matter. And another thing is, if we knew the score of every sequence from y1 to yn minus 1, we can then easily compute the score of the sequence y1 to yn. So this is kind of the core insight here. So we take advantage of the fact that we can calculate this recursively. What we really only need to know is we need to know the score of all the sequences ending in each possible candidate for yn minus 1. And if we do this, then we have yn minus 1. We can calculate the function with respect to yi, and now we've incremented one step forward into the future, right? And we'll think of that as some sort of pre-calculation that happens before we think about yn. So how do we actually do this algorithmically? The way we will do this is basically by doing a forward calculation using a dynamic program through the entire output. And I'm going to do this calculation in log space, not probability space. So up until now, and actually, I'm sorry, this is a little bit confusing. So the next couple slides, up until now, I was talking about this in probability space, so this had to be positive. Now I'm going to talk about this in arbitrary feature space. So all the slides here, when you look at psi, think that this is actually log, like log psi, and then we're going to be exponentiating later. So yeah, so sorry about that. I just realized that this is confusing, and I'll fix this in future iterations. So now we have two different feature functions. The first feature function is basically calculated according to this matrix. So this matrix says, given that the previous tag was our beginning of sentence, what is the probability of transitioning from beginning of sentence to noun? Sorry, what is the feature value for going from beginning of sentence to noun? What is the feature value for going from beginning of sentence to adjective, etc.? So another way we could look at this is we could take one row of this matrix, basically, and say that each of these red values here is a value at this red score. We could also look at the probability of the first tag being a noun, the probability of the first tag being an adjective, the probability of the first tag being a verb. It's sorry, I keep saying probability. I apologize. The feature value or the logit or something like that. So this is again in log probability space, kind of just a score indicating, relatively, do you think it's going to be more likely to be a noun, adjective, verb, etc. But this is not normalized into a probability. So once we've done this, now we have a transition probability and a transition feature and emission feature. And this gives us a score here. So now we have the score for time step 1 what is the score for each of these particular parts of speech tag in the vocabulary. So now the more interesting thing is when we take a step to step 2. So in step 2, now we know the score for step 1 based on our essentially recursive calculation. And then we can add all the transition scores and all of the emission scores and add them together with the likelihood that we, or the logit essentially, that we were in this space. In like the previous one was a noun here, the previous one was an adjective here. So basically this is considering all of the previous tags and all of the next tags. Oh, sorry, that's a, no, that's not a typo. Sorry, that's okay. Yeah, so this is the probability that, the feature that this is a noun and all of the transitions here. Does that make sense? And then the next thing that we need to do is what we really want to know is kind of the aggregate score, the aggregate log, log probability or unnormalized log probability that we were in this noun at time step 2. So what we do is we do something called log sum x, which basically exponentiates each value, takes the sum of them and takes the log of them. So what this is doing is this is basically calculating the features in log space and normalizing them appropriately. And then when we get to the very end, we know at the end of the sentence we'll have to have like end of sentence be our last token, or be our last tag. So we don't have any word here, and we essentially know with 100% certainty that this is going to be the end of sentence tag. So we only calculate our transition scores here, and we do a similar log sum x. So what this allows us to do is basically step through the sentence calculating the first feature value, every feature value between the start and the end, and the feature value in the end. And what this will give us, essentially, by the end of this calculation, is a dynamic program to calculate this partition function here. So this is taking advantage of the fact that you can calculate this partition function by like cleverly utilizing this independence assumption here. So this is the general idea. How you can actually write a dynamic program to do this. You can write all of this in like matrix operations, vector operations, etc. in your favorite neural network toolkit. This isn't an assignment, so you can go ahead and take a look at implementations. There's implementations in any toolkit that you would like to see, but it's actually not super complicated. It's basically you need to get the dimensions right, and you'll be able to calculate all of these in a nice vectorized way. So the way this works is then you calculate the score for the actual output. You calculate the sum of the scores for all of the actual outputs. You take the score for the actual output. You subtract away this partition function, and that becomes your log likelihood function that allows you to calculate the loss that you can then feed into your model. So if you read the CRF tutorial that I sent you all the way from front to end, you'll see that there's a forward step and a backward step used in this calculation. Interestingly, you only need to calculate this forward step, and then any neural network toolkit will automatically calculate the backward step for you doing backpropagation, which is kind of neat, right? Before you would have to calculate both the forward step and the backward step to calculate all of the expectations, etc. But this will, CRF toolkit will essentially do all the backward calculation for you. Are there any questions about this? Yes.
Not just that in the previous one,
Uh-huh.
the leftmost matrix that you draw on the board,
Oh, sure. Mhm.
Yeah. So how do you initialize the parameters in that particular matrix?
How do you initialize the parameters for this? So this is a good question. Probably the best way to do it is 0. And the reason why the best way to do this is 0 is that's basically saying a priori, I don't know how common transitions are, and I'll just let the model learn that on the fly. Another way, if you wanted to do it, in a more tricky way, you could probably calculate the empirical transition probabilities and do some sort of tricky math to figure it out. But I think in reality, people just set it to 0 and call it a day. There's no need to randomly initialize it, and the reason why there's no need to randomly initialize it is because this is not calculating hidden representations. It's rather just calculating transition. It's basically like a bias for your transition probabilities. So, a good question, though. Any other questions? Yes.
Can you elaborate a little more why we need randomization in neural networks?
Oh, why do you need random initialization in neural networks? So, like, I mentioned that neural networks are basically learning combination features. So the reason why learning neural networks with combination features is useful is because you can get feature hidden value number 1 in your feature matrix. Sorry, in your hidden feature vector to be like not positive word. Like not includes in the sentence and positive word is included in the sentence. The second one could be like this sentence seems to be about a human or something like that. The third one could be the sentence seems to be about vehicles or whatever. So like each value in the hidden vector of a neural network has some sort of meaning. If you do no random initialization and you just initialize everything to like 0 or something like that to a uniform value, all of the hidden vectors will get exactly the same gradient. And because they get exactly the same gradient, they'll completely covary, so they'll learn exactly the same thing. So random initialization basically makes sure that your features don't covary, etc. So, yeah. Yeah.
In the next slide,
Uh-huh.
I'm not quite sure what the subtractors from logs for.
Okay, yeah. So there's 2 ways you can look at loss functions. One way is in probability space, and one way is in log probability space. I have to apologize. Like some of the things here are in probability space, some are in log probability space. But basically, if we take the log, so this is kind of like the log version of the thing up there, right? So this would be the thing that you add. So this is basically the score for the true tag sequence, and then you subtract this kind of like log partition function. Sorry, it's EX. This log partition function, where the log partition function is exactly what I like demonstrated that you calculate if you calculate these values in log space. And so, sorry for the inconsistency here. The reason why the algorithm was using the log and the equations were using the product is if you use a product when you're calculating this in actual implementation, you'll get numerical underflow problems. Basically, the score will go to 0 or may go to 0 and then computation will fail. So in reality, you almost always calculate this in log space if you want to handle relatively long sequences. So yeah, I apologize for the inconsistency, but that's basically the reason why. Okay, any other questions or things like this? If not, I'll move on to the next one. So the next step is argmax search. So this is how do you find the optimal part-of-speech sequence according to the model. And the good news is the way of doing this is almost exactly the same as how you calculate the partition function. The only difference is instead of doing log sum x, you use the max at each time step. And so here, basically, instead of taking the sum over all of the probabilities, you're just taking the maximum probability. And at the same time, you take the argmax, and you save this as a quote-unquote back pointer. And what this does is basically, like, let's say, for example, noun was the max. What that would mean, or no. Yeah, I guess noun would, in this case, noun is the correct answer. So let's say noun was the max. That would mean we would be taking this first row here, and the argmax would be also like number 1, basically, right? So number 1, or 0 if you were 0 indexing. And what this does is if you go all the way to the end of the end of the output here, you would also take the max, you would take the argmax. And once you took the argmax, like let's say the max here was verb or whatever, you could then follow these back pointers. So you would say, okay, if the last one, the max was verb, so I'm going to go to verb for the previous time step. And then after we did this, after we went to verb for the previous time step, we would follow the back pointer from verb to the previous time step, and continue doing this until you can go all the way back through the sentence. And again, this is something, if you implemented the HMM type thing for algorithms for NLP, this is something you had to implement for that assignment as well. This is called the Viterbi algorithm also. Sorry, I didn't actually put the name. It's named after Viterbi, who was a famous guy who invented the Viterbi algorithm for coding and then went on to form Qualcomm, which is this big telecommunications company, and now the engineering school at University of Southern California is named after him because he gave them lots of money. So study your algorithms, study this class well, and you too might have an engineering school named after you in the future. Yeah.
So all this discussion was for first order CRFs, right?
Yep.
Yeah. Because
So
it's only depending on the previous one.
So this was all for first order CRFs. That's a good point. I'm going to talk about that in the future. So you're very, very good at predicting my future slides. Thank you. Okay, so I'm going to do a really quick case study. So this is kind of the state of, somewhat state of the art for sequence labeling. There are, I guess this would be the state of the art for sequence labeling not using pre-trained embeddings. It's still something that you definitely should know about and could potentially be useful even if you're using pre-trained embeddings. Contextualized embeddings. But basically, this paper, the goal is to build an end-to-end neural model for sequence labeling that beat all of the CRF models that were talked about in essentially the reading that you guys did here. And it's relatively simple. It didn't have any like feature template extraction or anything like that, where you have a character level representation according to a CNN and a word level representation according to a bidirectional LSTM. You have a CNN to extract morphological information such as prefix or suffix of the word. So you run a convolutional neural network over each of the characters in the word, and you extract the inputs for each of them. And then you do max pooling, where you basically take the max of each of these representations to calculate the representation for each word. This is then concatenated with a word embedding. So, it could theoretically be concatenated with a contextualized word embedding as well if you wanted to. This is fed through a couple layers of forward and backward LSTM, and then you have a CRF layer on the top. So basically, it's exactly what I talked about, except you need to implement the character representation as well. Yeah, I'll skip the training details, which are important if you want to implement it. But basically, they showed that the bi-LSTM plus CNN plus CRF on part-of-speech tagging improves like a little bit. On NER improves quite a lot. And the reason why it improves quite a lot on NER is because NER, it is actually quite informative. Like if you're predicting the in-person tag, it's very useful to know that your previous tag was a beginning of person tag, for example. So this is, kind of a standard tool in the toolkit that we use. So to get to the question, I was talking about linear chain CRFs. I'm not going to talk about this in a lot of detail. I think it's nonetheless interesting. So if you want to think about it a little bit more, I think this would be a great thing to think about for project-related things. But basically, you can think of a lot of data structures to marginalize over. One data structure that you can marginalize over is a fully connected lattice or trellis, which is basically our linear chain CRF. So each one of these dots represents a particular choice of a part of speech tag, and you're trying to find the best path through this lattice or trellis. And so you marginalize over all of the paths, but you want to maximize the probability of the correct path. Another thing you can think of is a sparsely connected lattice or graph that looks like this, where you're not actually fully connecting all of the inputs or outputs. There's a bunch of examples of this. So a bunch of examples of something that could be in this shape. One example is speech recognition lattice, for example. So like you have a speech recognizer, you output a whole bunch of different words, and you could do some sort of optimization over that. Trees are graph structures, so maybe they're a little bit different, but you could be doing some sort of marginalization over a tree structure. So there are tree-structured CRFs. Another one that I forgot to mention here that nonetheless is a very good one to know is something called a semi-Markov CRF. And a semi-Markov CRF is basically something that looks a little bit like I'll do T0, T equals 0, T equals 1, T equals 2, etc. And you can have a bunch of nodes. So this could be not an entity. Like, let's say we're doing this for named entity recognition. This could be not an entity. This could be person. This could be location. And then for our length 2 one, you could also have like person, location. Let's say we're doing named entity recognition with 2 tags, for example. And then you could also have person, location. So the reason why this is good is, like I mentioned, that we can create BIO. Let me put this higher so you can see it. You can create, you can do named entity recognition with like beginning, in, and out tags. Another way you can do it is just by saying I want to have transitions over like person, location, or something for the whole span. So what it would look like is if you had, person being Keanu Reeves or something like that. Your correct path, or let's say it was Keanu Reeves was, your correct path would then be a step from time 0 to time 2 that says Keanu Reeves was a person, and then a step from time 2 to time 3 that says was is not an entity. So this is called a semi-Markov CRF, and it's something that is also nice to know if you want to do kind of span labeling or something like that. Another thing that's more complicated, and I'm going to talk about it I think in 2 classes, is something called a hypergraph. So up until now I talked about graphs, where you're basically trying to take a path through through a regular graph. Hypergraph is basically a graph where you can have multiple input states to transition to an output state. And so then you pick either the orange edge, which says I'm transitioning from this state and this state, or the blue edge, which says I'm transitioning from this state and this state. This is useful if you want to like marginalize over multiple trees, for example. But I'm not going to go into this deeply because we're going to talk about it in a few classes. And then, of course, you can have a fully connected graph. So, for example, full sequence models are a fully connected graph. There's dynamic programming is not possible over these in their kind of unrestricted form. However, you can still think of them as a globally normalized model. And the only difference is instead of doing exact enumeration over all of them to calculate the partition function, you have to do some sort of approximation in order to calculate the partition function approximately to calculate the outputs. So yeah, so that is the, these are like some different examples. And if you want to calculate these, how do you generalize a dynamic programming model? You have to think of your decomposition structure. So basically, what local independence assumptions are you making? For the lattice, it was the linear chain CRF. It was saying, you know, over neighboring nodes. For semi-Markov CRF, it might be saying, I'm going to calculate the probability of spans, but I'm not going to calculate the probability of neighboring spans, or, you know, I'm only going to do one neighboring span or something like this. This also influences how you do a dynamic programming algorithm. Featurization, how do you calculate the local scores? Maybe the answer is LSTM plus something, transformer plus something. That's actually the easy part with neural networks. Also score combination. So how do we combine together scores? So like log sum x is one way to do it. Max is another way to do it. There's also crazy ways, more crazy ways to do things. So like, if you want to treat each score as a string and then combine the scores together by like concatenating them or something like that, there's actually very nice generalized algorithms that allow you to do this using a mathematical concept called a semi-ring. I'm not going to get into this there. But why am I mentioning this? And the reason why I'm mentioning this is there's a really nice library. I think I might have talked about it briefly before, but I'd like to talk about it again, which is this PyTorch struct library. And I have it here. And the nice thing is this basically implements a lot of things. So it implements your semi-ring, which looks like you have your standard semi-ring, which is in probability space. You have your log semi-ring, which is in log space. You have your max semi-ring, which is what you would need to do, you know, Viterbi search or something like that. And then it has a bunch of dynamic programming algorithms. Like it has your linear chain dynamic programming algorithm. So that can implement a CRF for you. But not only does it have linear chain, it also has the CKY algorithm, which if you've taken algorithms for NLP, you're familiar with. So this is a different dynamic algorithm with a different decomposition structure. So I think this is a really, really nice toolkit if you're interested in these kind of structured training algorithms with local independence assumptions. So I highly recommend it. So yeah, that's all I have for today.